Okay, guys. We are in our last chapter. Time maybe today and maybe next week to finish last chapter, and then we will go for review. Before we go for the chapter 9, I would like just to share with you that I need from you one scantron, red scantron, for the final exam. So the red scantron can be bought from the bookstore near you. In any campus bookstore, they have it. And near the bookstore outside, there is vending machine for food, and they put vending machine for this scantron. Now, the only logistics problems in this, before the exam, 1 day or 2 days, you will see the bookstore is running out of them. So just to be aware, to buy them before the exam, at least 1 week or so. So they have them 1 week. And the final exam is here, so you need to buy the red scantron, and the final exam will be Monday, December 12th. Monday, December 12th. So it's a little bit late because we'll end up the semester December 5th. And my online classes will have a final exam in the 6th and the 7th. But here you have more time to review. You have another 1 week to review. So that will be my last exam. The lab will be December, I think December 5th or December 6th or 4th. So the last day of the lab is the final exam. So the lab's no problem. Will be on time. But this one here will be the last day, Monday. So by Friday, the grade should be already submitted. So make sure that you book this one in, and then you know that will be final Monday, December 12th. The same time you start 1 o'clock. The final exam is 70 question multiple choices, and you will have 70 question, and you will have 120 minutes, 2 hours, I think, 120 minutes. So when it comes very close, then I will give you the whole thing. And the exam will be looking like any exam here. Those questions might appear similar to ACS exam. So those questions say with the answers, you can see the answers given to you here. You can see every time the answer is circled. But this is just to give you the sense on how is the final exam will be looking. So if you look at this review, and I think I put another review here. Let me see here. This one here, I'm not sure. Yeah, if you look at this, this is the mimicking, really, I would say over 80%. There might be the numbers might be a little bit different, but this is the final exam you can expect. The answers there, but this is the final exam. This is with the solution. But if you'll be not surprised to see those questions here, or similar to those questions appearing inside your finals. So I did not do this. Two faculty, they took study guide, $25 worth, and then look at the whole thing, and then start just not copy and paste, just modify a little bit, because you cannot copy and paste. That's copyright violation. So to get away from the copyright violation, if they put chromium and iron, they put copper and nickel. Are you following me here? So those questions are really very close to the ACS exam, but a little bit with modification. We cannot use them. We cannot copy and paste from the what they call it, from the ACS exam. But this is, and I'm not sure how many questions, but if you go all the way at the bottom here, those are 5. Yeah, those are 25, but the questions are 70 questions, 120 minutes. 70 questions, 120 minutes. So, and you'll be, and when we come very close, I'll tell you not to, what they call it, tell you not to keep anything blank. Now, there is a problem with the ACS exams. They will go and cover some stuff not covered in our book or in the ebook. For example, question number 28. So we did not cover it per se, but if I want to solve this one here, let me here just to let me get this sharing here and share just this share this question here. If I want to answer this question, how many sigmas, correct? And this is the answer here, A, B, C, D options. So, well, what you want to do here, here it is. This one here is, this is bi, double bond. This is another bi. This is another bi. This is another bi. And triple bond, they have two bis, correct? So if you look at this 1, 2, 3, 4, 5, 5. So bi here, double bond, including the triple, is 5, correct? Now the single bond, you have to be careful when it comes to this. This is single bond here. This is one here. Let me make another color. You can see. This is one here. Just bear with me. Did we cover this? No. Is this in Zoomdal? No. Is this in ebook? No. That's the disadvantage of this. Sometimes you want to test the knowledge of students if the students can. Yeah. So, but you do your best. So this is first here. This is 1. This is what? 2, 3, 4, 5, 6, 7. That's sigmas, single bond. So how many? 4, 5, 6, 7. So 3, 1, 2, 3, 4, 5, 6, 7, 8, 9, right? 10, 12. And here you have 3, 12, 3. Those hydrogens with carbon 3. 12 and 3 is 15. Are this the final exam? No. Is the final counting? No. The double bond itself made of single bond and double bond. So there is one here too, hiding. One of this double bond is single bond. One is here, correct? One is here, double bond. One is here. One is here. So somebody will count them. Let's make another pen here. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, and here's 1, 17, 18, 19, and here's 1, 20. Right? So if you count them to 20, maybe I discount. So it looks like 21. So let me, I said 21, but let's see, count them again. Let's count them again. The answer here from the book, from the 21. Let's count them. 1, 2, 3. That's double bond and single bond. So they have to, right? 3, 4, 5, 6, 7, 8, 9, 10, 12, 13, 14, 15, 16, 17, 18, and 3 here. And 3 here. That's 21. That's correct. 21 sigmas. And the pi, let's count the pi again. The pi is 1, 2, 3, 4, and the triple there has 2 pi, 6, not 1, 2, 6. So here is 2 of them. Here's 1, here's 1, here's 1, here is 1. So this is 6. So the answer is this one. The question to you is, did we cover this one here in the book? No. That's what the sometimes ACS exam will give you a question you have never seen. But you make educated guess and do your best. The triple bond is made from 2 double bonds and 1 single bond. So those questions you have, and similar to those questions might appear. So let me just stop sharing, go for our lecture here. For those who have done quiz number 3, exam number 3, the answers now are open. I open for you the answer. Go and check your answers, and if you have any questions, just let me know. Okay. So, what's units for the pressure we can use? Well, we can use plenty of units, but the main thing is it has to be SI or metric. That's what is used. For the metric system, we are using what? ATM. So this is the metric here. So this is the unit here for metric. And for the SI is this one here. So those are the most important units. But it does not mean an old units cannot be used. So in the lab, the barometer here can be using mercury, and it's labeled 760 millimeter mercury, correct? So millimeter mercury, so 760. So all those are equal the same thing, or 760, and we double capital T. Why is capital T? Because anytime we honor scientists, we use his or her name, and the name has to be capital. Remember joules? When for the heat, we say joules, capital Joule. So Dr. Joule here, unit is joules, it's blue, but singular here. So because it's a scientist, we honor this person, capital J. Here's just a typo, it has to be capital tall. Every time you use a scientist name as a unit to honor this one here, you have to have the capital T. And there's many, like Fermi. This is for the bonding, electrical bonding between layers. Fermi is capital F. So you can Faraday, capital F, correct? Capital F and maybe R. So all those names has to be. So those are all units equal the same thing. And this is the English one. The English one is PSI, pounds per square inch. So all those are equal the same one. So if I say I have 1 atmospheric pressure, that's metric, correct? And as I said, this is SI and this is metric. All the other ones are old, and this is English. So this is English here, and this is SI system, and this is metric one. This one is metric. So the metric. So this is the same units. The problem with this chapter is about unit. We have to conversion between units, whether this is English, metric, or SI. So you have to watch your next exam will be, I'll put the next exam, the last day for the next exam is the last day of the semester. So if you look at the, not sure if I put this one here, but it's already off. No, it's on. So if I say here, I just want to show you the exam here. Exam 4 and quiz 4, they are hidden from you. You can't see them, but I put them. What's the due date for them? The due date is December 5. So please, when even if when we finish, we go for review. Do not come and jump and then start answering the questions. So you have until December 5. So you have over almost 3 weeks or more than 3 weeks. So take your time. Those are 3 chapters. That will be the last exam and quiz you will have. You will not have after anything. So after that, no exam or quiz anymore. So put this one in December 5, and this is you have plenty of time. So let me here come and share again the. So now let's look at, we looked at the units, and we said all those are equal. All those units are equal this. So all those units are equal this. Although metric, but the atmospheric pressure is used, I mean, internationally everywhere. So the atmospheric pressure, but some countries, they use like the English system, the PSI. Kilopascals are just in the textbooks. Kilopascals, not use it in, but most is you have, those two are heavily used. Atmospheric pressure and the PSI. So looking at this, pounds, correct? That's a force. Square inch, that's an area. So this is area here, right? So you can see here, this is an area, and this is a force. So if you divide those together here, right? So you get what? Get something called pressure. So the pressure is force per area. Now you tell me which one of those will have, the largest pressure, and which one will have the smallest pressure. So look at those 3 different shoes, 3 items, not shoes. It's like a, 3 items. 2 of them shoes, and 1 of them is like a tennis rack. So which one? Somebody will tell me which one is the highest pressure. Now look at this formula. What did you say? The area. So look at the area. This area is the smallest, correct? This area here, it's not spread out. This is the smallest area. When I say the area of my hand, is all this space underneath my hand. So this is the smallest one. This is like a kid's shoe. This small area. So if you have this area is small, the pressure will be what? Very high, correct? If you have like this, area is huge. This is the largest, correct? Smallest, this is the largest. So if you have this largest here, guys, so, and therefore, the area will be very large. So this one here, so this one here, and this one is here. Are you following me here? If you assume that the force, we'll keep the force constant. We'll look at the area because we don't know the force. We have no mass. We don't weigh those. We did not weigh to determine the force, but we can tell by inspection about the surface area of their area underneath. The area of those 2 racks here, 2 tennis racks, are large. So therefore, if it's too large number here, correct? Suppose you say the area here is 2 or 22 meters square. Just show you here. And here is 2 to 5 meters square. and this is whatever is for the force can be in as energy, kilojoule, or in any other type of them, correct, or pound. So if you look like this is small. If you divide any number, it's constant, by a small number, the number will be large, correct? If you divide by a large number, the number will go down. So the larger the surface area, the smaller the pressure. So those more tiny kids' shoes will have the largest pressure. Are you following me here? Everybody's following me? So that's what it says. I mean, that's, you have to look, look. This one here, this type of shoes here, that's moderate, in between those two. Medium pressure, not high pressure. So, but the smallest, those kids, those children shoes, because of their smallest area, therefore they will bring higher, they will cause higher pressure on the feet of the children or the kids. So it makes sense? Any question about this? Okay, but just the conclusion is the higher the area, the smaller the pressure. Those are indirect proportional. The smaller the area, the higher the pressure. The higher the area, the smaller the pressure. So this indirect proportional. So now about this. Well, you can tell this in 1800, Boyle is a French scientist and physician, doctor, chemist, physicist. He holds too many degrees at that time. You can be, 5, 6 degrees at the same time. So, but nowadays you can't. In chemistry, you have about 10 or 15 special areas. You cannot take all this. But at 1800, he is a physician. He had discovered this some bacteria. He worked with some bacteria that make the food bad. He had done gas laws, so he had a lot of stuff between physics, chemistry, and physics, chemistry, and medicine. So he had, as I said, longer time that you can't do it because the science is not really spread out and specialized in areas. Now in medicine, you have hundreds of areas. Just look at the cancer medicine. Then what? You have cancer of the brain, cancer of the skin, cancer of the liver, cancer of the kidney, cancer of this cancer. And all those are special areas for each students who want to study. You cannot study all cancers nowadays. You have to specialize in some specific areas. So nowadays it's very hard to know everything. Very hard. So Boyle's started the gas law, and this gas law says, same thing we did with the pressure and the area, correct? He said, if I have the volume of a gas is increased, the pressure will decrease. If I decrease the volume, pressure will increase. So if I have a piston here, correct? See here, base. If I put too much pressure, what will happen to the volume? The volume what? Will go less. If I release the pressure from the piston, so the volume will increase. Are you following me here? So what it means the pressure and the volume of a gas are indirect proportional. So if you increase one, the other one will decrease, and vice versa. So that's what his law here. If you look like this is the relationship. So this is the relationship. The relationship is not linear. Can I make it linear? Yes. I take this one here, the volume in y-axis, but here in the x-axis, I put 1 over p because that's indirect proportional. So if I put 1 over p, then I get this a very nice linear relationship. But if I put just v and p here, I get something looking like this. It's not linear relationship. So what I want from you here for the next exam and for the final exam, you have to memorize it. This is, you're not allowed to use any flashcards. This is, you have to put Boyle's law in a flashcard or a piece of paper. And what is this law? This is, you have to memorize for the final exam, and but at least for the exam number 4, you have to know. This is Boyle's law, meaning if you increase the volume, it's indirect proportional to the pressure. Now you can get this indirect sign. The volume, correct, is equal constant for constant, correct, over the pressure. So the volume and the pressure cross multiply equal constant, correct? This is the law. I'm driving the law for you here to see how does it look like. So this is Boyle's law. So constant over P, indirect. So if you look like this, so you'll have this one here equal to this, to here, sorry. Equal what? Constant, correct? Equal constant. This is Boyle's law. It is. This is Boyle's law. Meaning this one here means here, when I say this one here, that will be my initial state or condition, initial state or condition. And this one will be, number 2 will be my final state or condition. So this is final. Okay, so at least you don't know all the details, you don't have to, but the main thing is for me is, let me take, the main thing for me is this and this. And you know, 1 means initial condition or state, 2 means final condition. So this is the first law. Now let's look at the all examples we have. Boyle's law. So here it is. So they give you the other balloon with the volume of this one. So therefore I'll say, okay, this value here be my V1. That's the initial one. At the pressure of kilopascal is, this is my V1. Rises to an altitude of 1,000 meters. This is, we have nothing to do with this. We're not calculating the altitude, but as you see, if you go higher, the altitude of a lot of physical properties will change, correct? Tell me what's the boiling point of H2O at 1 atmospheric pressure. If I'm in Savannah now, if I want to boil the H2O, it boils at what temperature? That's sea level, correct? So H2O will boil at 1 atmospheric pressure at 100 degrees. But if I go to the Rocky Mountains in Colorado, the top of them, what do you think? H2O boils at 100 degrees? What do you think? No. Boiling there maybe 75 degrees, depending what the moisture and those other stuff. So you go higher in altitude, the boiling point will decrease. You go closer to sea level, like Savannah here, close to sea level, the boiling at 1 atmospheric pressure will be 100. And all our references is always at 1 ATM. Boiling point, freezing point, sublimation point, and condensation point, boiling point. All those points are at 1 atmospheric pressure. So just to let you know that we are not dealing with this altitude, but you know the altitude plays a major role in physical properties of the compound, of the matter you are dealing with, like H2O. Boiling point. So sea level is 100, 1 atmospheric pressure, 100 degrees. You go higher altitude, then it's about 70 degrees. So then if you go even higher and higher than the Rocky Mountains, will be maybe around 50, 45, 40, start boiling. Right? So then, where the atmospheric pressure to be, this is your V2, right? This is your V2. Assuming there is no change in the temperature or amount of gas, calculate the weather balloon final volume. So this is between the relationship between the pressure and the volume is Boyle's law. Immediately you'll know from your flashcard or this piece of paper in front of you, I have pressure and I have volume. The relationship is Boyle's law. You have to memorize this before the final exam. You are not allowed to bring anything in the final exam. And we will be like a hawk on you. So two professor, me and another one will help me with it. So I want you to memorize this before the final exam, because this is, we don't want this to be leaked out this exam. So therefore you'll see more restriction than now we have. So you are prepared. So if I have the pressure and the volume, this is Boyle's law. Boyle's law will tell me the initial states will equal what? The final state. Correct? It said, what's the final volume? It said the final. This is my final, correct? So both sides by P2. I divide both sides by P2, correct? So therefore, P2 out. So V2 will be P1 divided by P2. So P1 is given to you. This is 96 or 96.3. I have to watch for the units, guys. Watch for the units. And this is 2000. I'll put a decimal here. So this is liter, this is kilopascal. Kilo, small k, kilo, and then Pascal, PA. So P2 is 60.8 kilopascal. So the kilopascal of the kilopascals would cancel out as a unit. Cancels out. You have 96.3 multiplied by 2000 divided by 60.8. So that will give you the final value, correct? That will give you what the final volume. So now the second law, the second gas law, called Charles. So again, those in 1800 scientists, they were multi-rich scientists. They were most of the time physicists, chemists, and they were physicians as well. So they gather large range of degrees. So that's very good. And some of them even geologists, and some of them are astronomists, besides whatever they are. So they are really good. So Charles is one of those scientists, the same thing like Boyle's. So Charles had seen that by experiment, if I increase the volume, if I increase the temperature, what will happen to the volume? Will decrease or increase? If you heat a gas, what will happen? This gas molecules will spread out, correct? And its volume will increase. So meaning what? Charles is telling us that the volume of a gas is direct proportional to its temperature. The higher the volume, the higher the temperature. The lower the volume, the lower the temperature. So that's what it says. So direct proportional. And as I said, if we want to look at this, so V is direct proportional to T. So I can take this one here to get the constants. First multiply V over T equal constant, correct? Equal constant. You don't have to write this after me, but at least I just show you how we drive this relationship. So the higher the volume, the higher the temperature, and vice versa. So direct proportional means the sign of direct proportional can be transferred into, so I took this one out and replace it with equal constant. Correct? That's what it says. So now I can say, well, if that's the case, then I have Charles' law will be V1 over T1, correct, equal V2 equal T2 equal what? Constant. Equal what? Constant. So here it is. So this is Charles' law. This is Charles' law. So temperature is direct proportional to the volume. So if I go here, the next slides, and this one, what I wanted to make a second, I mean, after boils, put this one here and put this one here. And 1 means initial and 2 means final. So you have to put those here and you memorize them for the final exam. Is the gases are coming? Yes. And those are more than one question, maybe 2. You have 70 questions. So the gases is very important because they will come with you all the time. So depending on what you are specializing, if you are specializing in the area, you are working with the gases, then you learn more about this gas laws. So this is to be memorized. For the time being, put them in handy for you for the next exam, but you have by the final exam to memorize this. Charles' law says the higher the volume, the higher the temperature. The lower the volume, the lower the temperature. Correct? So let's look at the example here. So with this one here, the same thing we did with boils. So let's look at this example here. Example. I look at the key information given to us. Here it gives to us what? Volume 1. And this is temperature 1. Relationship between volume and temperature is Charles. You have to memorize it. Pressure and volume boils. Temperature and volume is Charles. So then I just put this whole thing here, V1 over T1 equal to V2 equal T2. Okay, guys? Sorry. So V1 is 1.5. So I have 1.5 1.5 L, correct? Temperature is 293, capital K. Kelvin is always kilo small, but Kelvin has to be capital. Okay, equal to, and give you the volume. The volume 2 is given to you. This is here, your V2. And then it's asked for you T2. T2 is question mark. So you don't know. So this one is 1.55 liter L over T2 in Kelvin. So the liter with the liter cancels out. Cross multiply. So the T2 here will be, I'm not calculating, but at least set it up. T2 will be 293 multiplied by 1.5 5 and the whole thing divided by 1.5. So, and this is K, capital K. So that will give you, the calculation will give you T2 in Kelvin. The T2 will be what? In Kelvin. So this way we can calculate our T2 in Kelvin. So the relationship between volume and pressure is Boyle's. Temperature and volume is Charles. Now we know to something called, we'll have to have still two more or more than that, but at least two more name of scientists, Avogadro's law and Gay-Lussac's. So Gay-Lussac's will tell you this quite the opposite of the Charles. Charles said temperature and volume. Gay-Lussac's say no, temperature and pressure. So Gay-Lussac's gets it. If I have the pressure is very high, the temperature is very high. If the pressure is very low, the temperature is very low. So quite different from Charles, but Charles relate the volume to the temperature, and the pressure is related to the temperature through Gay-Lussac's. And here it is. Take this one out. Again, all those gas laws, most of them are covered in the 1800s. So as I said, so here it is. Gay-Lussac's is telling us that the pressure, the pressure is direct proportional to the temperature, correct? So I can take this one here, the proportional to equal, and then equal what? Constant. So this way, always take the proportional sign and replace it with, so this one here equal this. So P over T equal constant, and the relationship is direct proportional, means linear. The same thing with the Charles law. So the higher the pressure, the higher the temperature. So there is linear relationship. So that's linear here. Linear relationship. The same thing with Charles. Charles is linear. Now looking at this, then you have P1 over T1, that's initial, equal to T2 equal T2. That's final. So this is Gay-Lussac's gas law. Final state or condition, and P1 or 1 is initial. Okay, so and this here I want to again, this one here, put it in what? Now how many we have? We have 3. This is in the flashcard or in the same piece of paper. Put this law together. So you have Gay-Lussac's law and direct proportional. So here is equal, by the way. So that's equal to. Make sense? This is Gay-Lussac's dealing with the pressure with temperature. So now I don't see Avogadro's law. Avogadro's law, okay. Avogadro's law will come in a couple of minutes. But let's take this one here. STP. STP means standard temperature and pressure. What are those STP for a gas? Well, it turns out to be, let me go here and so I can change the color so you can see it here. It is so you can see it. So what is standard temperature? Standard temperature is 0 degrees, which is 273.15, or you can take the 0.15 out. This is Kelvin. 0 degrees means 273 Kelvin. 1 atmospheric pressure, or that's metric, or 101.3 kilopascal. So those are the standard condition. What's unique about this standard condition? At standard condition, so let's write it here. At here. Let's write it. So here it is. At STP, and thus you have to put it in a piece of paper again. This is here. At STP, correct? 1 mole of the gas will deliver any gas. 1 mole of any gas. 1 mole. 1 mole of any. Does not really matter to be. Any gas will give 22.4 liter. So this is very important. Standard temperature and pressure is 0 degrees, 1 atmospheric pressure, correct? So those are, at this condition, the gas volume has to be 22.4 liter. The contribution of this this law goes back to Avogadro, right? Goes to Avogadro's, and therefore we can go and look at the Avogadro's law. Well, Avogadro's law is, it's not written here very, very well, but it says the volume of a gas is direct proportional to a number of its mole. So this is mole here, moles. And this is volume. So this is I'm writing with the mouse, so I apologize. Not my handwriting, but trying my best. So the volume is direct proportional to what? To number of moles of a gas. Volume of a gas, direct proportional to its volume. So I can say, well, V1 over number of moles 1, the first initial, equal V2 equal N2 equal constant. And going here, this is Avogadro's law, gas law. So Avogadro's law will tell you that the volume of any gas is direct. It's not in the it's not in the PowerPoints, but it might be in the ebook there. But this is the Avogadro's law. And then another Avogadro's law at the standard condition. This is another one. That's what we said. So any mole of any gas, any mole of any 1 mole of any gas, give us what? Give us 22.4 liter. Any one mole of any gas. So we have, this is number 1. This is number 2. Write it down. Write them down in a piece of paper. Yes. Yes. The pressure has to be constant. When you look at the whole thing, The other stuff here, like we did not consider, the other stuff here, let's put this one here. The other stuff is pressure, correct? And temperature. Are they included? No. So therefore they are constant, not change, no change, no change. Correct? No change. Okay. No, we keep them unchanged. But the same thing with the other laws. The same thing with other laws. Let's go back and look. Let's go and look. Okay. So you have this one here. P and T are no change, means they are constant. They are what? Constant. No change in them. So if I go back all the way to Boyle's, so you tell me what's now happening here. All the way to Boyle's here. Here, look at this. This is Boyle's law, correct? So what we are not mentioning is number of moles, correct? This is number of moles, number of moles. What we are not including, temperature. So they are kept constant, no change in their values. And that's what it said, assuming the temperature is constant and the number of moles are, both of them are constant, correct? So go to Charles. Charles. This is Charles, correct? So what we have not considered here, pressure, correct? Not there. And what? Number of moles. Those are constant. Correct? So here it is. Let's go and look at Gay-Lussac's. So this is Gay-Lussac's here. This one has to be equal. So this one here, what we have kept unchanged, not even touched? Volume and number of moles. Those are constant. Here, this understood, the volume is not changed, just they go for volume is remaining constant, but the number of moles are constant. Then we come back to Avogadro's stuff. Avogadro's here, and which is volume over number of moles equal this initial, final. What we kept here constant. P, the pressure is constant, and temperature, not part of the whole thing. So they are kept constant. Make sense? So now if we combine, and this is the first, this is here, Avogadro's, this is another one law of Avogadro's. 1 mole of any gas will deliver 22.4 liters as a value at STB. STB, standard temperature and pressure. Temperature is 0 degrees or 273.15 Kelvin. Pressure is 1 atmospheric pressure, 1 atm or 101 kilopascal, 101.3 kilopascal. So now, if you combine now Boyle's, let's look what Boyle's is. Boyle's, somebody will tell me, somebody remembers, what's the relationship? Boyle's. Between what? Volume and Pressure, correct. Indirect proportional. Charles will be volume and temperature. Perfect. Then Gay-Lussac, what will be? What will be? Pressure, correct? Yes. Pressure and temperature. Then our friend here, old friend Avogadro's. Avogadro's will be what? Volume and number of moles. So if you combine those four, then you will come up with ideal gas equation, and you come up with a law called combined gas law. So the combined gas law is nothing really new. It's just you add all those up and you work them out. And guess what? If you have all those relationships, you will come say, okay, so I can come up with the new law. It's not really a new law, but I can say it here. Here, let me just do it here. How about I say, for example, P1 over V1 over T1. So I'm combining all those three laws, P2, V2, and T2. And that's what we have here. This is combined law. So this is a combined law. You don't have to memorize, because if you know that what's given to you, just you can do it, and you can do it, and you can the whole thing. So let me show you just an equation here. So this is a combined law. But if you have an equation called PV equal N number of moles, R is the gas constant, T Kelvin, correct? That's initial say 1, and this is 1, T1. R is a gas constant, does not change. So you divide it by final, correct? N2 R T2. Now the gas constant here is not changing, so you can take this one out, take the R gas constant out. Okay. You can take those two out. You have, and you assume this is for one gas. The number of moles is not changing. They are equal to each other, so you can take this one out, this one out. So N1, number of moles is not changing for one gas. So number of moles are the same. They are equal, so they are out. So what you will end up having, V1 equal P2 V2 equal to P1 over T2. Cross multiply. Cross multiply, you get this one. Cross multiply, you get this one. So this is combined gas law. It's coming from the ideal gas, or you can combine all those three laws together, including Avogadro 4 laws, to get them there. So guys, so you can write this one here in a piece of paper, this law here, especially this one here. Write in a piece of paper, that's a combined gas law. So how you know this combined gas law? Let's look at the example here, guys. It says a gas occupies, you have here, see here, you have This is V1. This is P1. This is T1. Find its volume at STP. So if you have three variables are given, so you know that's a combined flow. Three of them together are given. So first of all, you have to be careful about the units. And this is a very good chance for us to look into this, correct? A centimeter cube here, guys. Let's look at the example. 1 centimeter cube is equal to 1 ml. So 1 centimeter cube is 1 ml, correct? So if I said 1 milliliter, this is milliliters. So if I want to change this one here, 7.84 centimeter cube, correct? This is 7.84 milliliter. But I need this one here, and this you have to always remember. Volume always in liter. Temperature always in Kelvin. Have to convert them. So volume has to be converted in liters, temperature in Kelvin, and this one here in kilopascal or ATM. So here it will be in 1 ATM. So correct. So now going this, let me just take this one out. It has it. You'll have it. So this one here will be B1 equal to 7.84 10 minus 3 liter. Okay. Then you have, I need this one here because the gas constant is always R. So said what? I can keep kilopascal because I will be using the 103 kilopascal as well. So I can keep this one here. Keep. So P1 is 71.8 kilo pascal. Temperature is 25, and we have to watch for this, plus 273.15, and this one will be 298.15 Kelvin, capital K. So now we have everything there. How about the STB? Our STB here is temperature is 0 degrees, which is T2 273. .15 Kelvin. And the P1, since we used the kilopascal, so this one will be, that's P2 here, 101.3 kilo K pascal. Correct, guys? So now set up the whole thing. P1 V1 divided by T1 equal to P2 V2, T1, T2 here. Let me take this one here out. This is T1. So all those are given to you. All those except V2. V2 here, V2 is question mark. So just put all those in and plug for P2. So this one here is given to you, 101. This one here you don't know, question mark. Temperature here is 273.15. This one here is 298.15. Pressure is here 71.8. And the volume is 7. This one here, this value here is this. There's no space for it. But here, and you work it out and you solve for V2. That's what the whole thing is. This is a combined law because you have all those given. 3 of them are given, correct? All the problems is only 2 given only. The third can be solved, but here 3, and then from 3 are given. Then you can remind yourself this has to be combined law. Now, the topic here after that is ideal gas. Ideal gas. Well, question to us: do we have a gas is ideal gas? No, we don't have an ideal gas. All the gases are behaving real life. There is no ideal gas, but we can force a gas to behave ideally if we have some conditions, extreme conditions, which is where we can find this gas can behave, like the sun, stars. The sun gases, they behave ideally because you have to have very extreme temperatures. When I say extreme, that's like 20,000, 100,000 centigrade Celsius. So there's no barbecue. You put anything inside, correct? That matter here will be just disappearing as vapor. So now no bones, no. If you put a human in this temperature of the sun, I can guarantee you there will be no barbecue. You cannot even see the person. It will evaporate. Nothing will be out left. So if you say ideal gas, well, there is nothing ideal gas, but we can force a real gas to behave ideally. If you put this gas in a very, very extreme temperature, in the sun you have thousands of high temperatures or stars, and then you have very, very low pressure. So that's when you force the gas to behave ideally. But in the real life, do we have a gas behaving? All the gases are behaving like a normal real gases. They can't behave ideally, but you can put them in a condition, they will start behaving ideally. So that's what's you can say here. This an ideal gas. So what do you think about an ideal gas? Well, it's a gas, it's a real gas, put in ideal conditions, in very extreme conditions, which are higher temperature, extreme high temperature, sun or stars temperatures, and very, very low pressure. So the pressure on the suns are very, very low, but very, very high temperatures, right? An ideal gas follows the gas laws at all conditions of pressure and temperature. Behave according to the kinetic molecular theory, because that's the temperature when all those molecules, correct, all the molecules are spread out. So does the ideal gas exist? As I said, there is no ideal gas. All the gases are real, but you can force them to behave ideally. And those sun gases such as methane, hydrogen, what else? All the hydrocarbons, those the sun can be present and can be behaving ideally. So real gas behaves as an ideal gas at high temperature. That's a star. When I say high temperature, it's not a normal temperature on the Earth. It has to be very extreme temperature and very low pressures. So real gases differ from an ideal gas at lower temperature and higher pressure. Do not follow gas law at these conditions. Well, if you put the gas very, very low temperature, what will happen? This gas will come at a 0 Kelvin, this absolute zero temperature. Everything will come and freezes. All the molecules will stop motion. They don't move. So that's the gas, that's a real gas will do. That's a real gas will do. When you put very, very low temperature and very high pressure, and this will come together to make, out of this gas, you can make solid. I'll stop here, and then next time we'll go for ideal gas law. We'll talk about this. I'll stop. So, just a reminder here, I put the answers of the quiz 3 and exam 3. They are open. Look at the answers. They are now open.